Ladies and gentlemen, we have two special colloquiums today, and we're very happy to have Pavel Galashev from MIT, who speak on Ising model and total productivity.
Thank you. Thank you for the invitation. So this is a joint work with Pylyavskyy from Minnesota, and first I'm going to tell you about the Ising model, and then I'm going to explain how to relate it to total productivity. So I'm going to start with the definition, and the definition is pretty elementary. So there are different generalities you can work in. I'm going to be, for me, it's going to be convenient to work with planar Ising networks. So what is a planar Ising network? Well, it's a pair G over J, where G is a planar graph of any disk. So it's important that some of the vertices are in the boundary, and then the rest is drawn on the side without top sections. And J is a map. Well, it's a map. It's an assignment of positive real values to the vertices of my graph. These numbers are called interaction constants. And I'm going to think of the vertices of my graph as atoms, and every atom is going to have a spin. So a spin configuration is an assignment of plus and minus 1 to the vertices of my graph. And the Ising model is a probability measure on this set of all spin configurations. So there is 2 to the number of vertices spin configurations. Each of them gets a probability that's going to be proportional to the weight. And the weight is given by this formula. So let me rewrite it in a little different way. So the weight of a given spin configuration is just the product over all edges of my graph. And then for every edge, I'm going to either multiply by the exponential of the interaction constant if the spins are the same, or I'm going to divide by the same exponential if the spins are different. And okay, so for instance, the weight of this spin configuration here is the exponential, the product of exponentials of the red edges divided by the product of exponentials of the blue edges, where an edge is red if it connects vertices of the same spin, and otherwise it's blue.
So this is ferromagnetic?
Yes. Thank you. Right, so this is the so-called ferromagnetic Ising model, which means that the interaction constants are positive, and it's important because if these are positive, then the exponential is bigger than 1. So if a spin configuration has a lot of spins which are the same, then it gets a higher weight. So the most likely configuration is the one where all the spins are the same. And now, okay, so these weights, they don't sum up to 1. So we should introduce the partition function, which is just the sum of the weights of all spin configurations. And then the probability of a given spin configuration is just its weight divided by the partition function. So we have some kind of nice probability space, and we can ask questions about expectations and covariances. So I'm going to be interested in correlations. And just by definition, the correlation between the vertices U and V, which is denoted by these square brackets, is the probability that the spins at these vertices are the same, minus the probability that the spins are different. And because of our observation that this is a ferromagnetic Ising model, right, the spin configurations with a lot of spins are aligned, they get higher probability, it seems kind of natural to conjecture that these correlations are always positive. And this is true. This is not trivial to prove, but it was shown about 50 years ago. So not even in the planar case, just arbitrary graph, these correlations are always non-negative. And then a year later, there was a paper by Kelly and Sherman who proved some more general results, and an example of their result is this triangle inequality. So for any 3 vertices U, V, and W, the correlation between U and W is bigger than the correlation between U and V times the correlation between V and W. And in the same paper, they asked the following question. So we have some interesting inequalities. Can you find all inequalities? So if I let's say I have 10 vertices and I give you all pairwise relations, can you tell whether they come from the Ising model or not? Like one thing you could check that this inequality is satisfied for any trivial vertices. And if it's not, then they don't come from the Ising model. So this question stayed open for 50 years, and in this generality it's still open, and many people proved many different inequalities. One of these people was Martin Wyss, who recently wrote a paper called Ising model and total stability. And this paper he found some bijections between combinatorial logics for the Ising model, like random currents, and some combinatorial logics from total stability. And he showed even more general inequalities. And we studied his work, and we came up with our construction. And one nice corollary of our result is that we can now answer this question in the planar case. So if you give me all pairwise correlations between boundary vertices, then there's a very easy to remember set of inequalities which tells you whether there exists a planar Ising network with these boundary correlations. So this was kind of a preview, and let me now start from the beginning and tell you about the history of the Ising model. So the Ising model was introduced by Lenz, who suggested it to Ising, who was his PhD student. And Ising wrote a thesis on the Ising model where he came to the conclusion that it is not an interesting model for magnetism. So what does that have to do with magnetism? Well, so let me propose an experiment. Let's say I take a piece of metal on a wire, and you can actually do this at home. I actually tried. And you take a magnet, so the metal gets attracted to the magnet with some magnetic force. And then you take like a candle or lighter, and then you start heating up your piece of metal. And you ask, well, what's going to happen to the force as the temperature of the metal increases? Does it become more magnetic or less magnetic? And the answer is that it becomes less magnetic. Right? So the force decreases as the temperature increases. But there are different ways it could decrease. It could be smooth like this, or it could be there could be some kind of crazy singularity going on. Which one of these pictures do you think is the correct one? Yeah. So the second picture is correct, and the first one is not. And this is called a phase transition. So it's a sharp change of properties as you go a little bit above the critical temperature. And this temperature is called the Curie point of your material. And you can see it was discovered 25 years before the Ising model was introduced. So people were looking for a good mathematical model for magnetism, and a good mathematical model should exhibit a phase transition. And what Ising actually did, he computed everything correctly for the one-dimensional Ising model, where your graph is just a path, and then found that there is no phase transition. So he wrote something like, my argument generalizes to higher dimensions, so this is not an interesting model. And by higher dimensions here, I mean that usually people don't just take an arbitrary graph, but they take something like a square grid, or a more general lattice. And they also don't consider just arbitrary interaction constants, but they set them all to be the same, just one temperature. And so people started looking for different models. Famous people like Heisenberg proposed alternative models, until 12 years later, Pylyavskyy gave a very simple argument that there must be a phase transition in all dimensions higher than 1. And 4 years after that, Kramers in 1 year found the exact value of the critical temperature for the square grid. So I gave you kind of a physical explanation of phase transition. Let me also give you a mathematical statement. You can prove many theorems about this phase transition because a lot of properties change. So here's like the simplest kind of theorem. Let's say I take a large square grid, and I consider the Ising model with plus boundary conditions. So I just force all the spins on the boundary to be equal to +1. And then I take a vertex in the middle of the square, and I ask, what is the probability that I also get a plus in here? And because, well, more precisely, let me define this quantity called spontaneous magnetization, which is the limit as the size of the square goes to infinity of the difference of these two probabilities. So it's kind of like the correlation between the boundary of the square and the middle of the square. And because the spin of this vertex depends on its 4 neighbors, and then when all of them are plus, then this vertex can still get a minus, it seems kind of intuitive that this limit should always be 0, at least to me. And this is true, but only if your temperature is above the critical temperature. So when the temperature is below the critical temperature, there are some long-range interactions. And by the way, as the temperature approaches the critical temperature, the magnetization depends on the difference raised to the power of 1 over 8.
So 1/8 is an 8-dimensional?
That's not, I think that's just 2-dimensional. Okay, so let me now go back to the history slide. As I just said, these people, and most notably on Sagar in 1944, he found the exact formula for the free energy, and then since then there has been like tens of thousands of papers on the Ising model, and I'm not going to be able to review all of them today, but let me just mention a couple of groups of people. So Pylyavskyy and Lusztig, they gave some predictions that the scaling limit of the Ising model should be described by conformal field theory. It should be conformally invariant, things like that. And then some of their predictions were proved by Smirnov and Karp and other people, in particular the conformal invariance for the scaling limit at critical temperature for the square root. And this is all very important stuff, but I'm not going to talk too much about this, but I do think it's going to be later. It should be related to the stuff I'm going to be talking about. Let me just go back to my original setup, which is much simpler. We just have an arbitrary planar graph embedded in a disk. And for me, the little n is always going to denote the number of boundary vertices. So in this case, n is equal to 6. And I'm interested in these correlations. So let me define a boundary correlation matrix. And they're denoted by m of g, j. This is the boundary correlation matrix. So this is just an n by n matrix, right, where the ith and jth entry is the correlation between the ith and jth boundary vertices. So a few observations about such matrices. Well, this is a symmetric matrix. Mij is equal to nji for obvious reasons. And also it has ones on the diagonal. Again, this is clear from this formula. And the off-diagonal entries are between 0 and 1. Right? They're non-negative by this inequality, and they're close to 1, again, from this formula. So these matrices, they live inside an enters 2-dimensional real space. And inside that space, let me denote by x of n. So x of n is going to be the space of all n by n boundary correlation matrices. Right, so I take all possible planar graphs in a disk with n boundary vertices. There's infinitely many of those. And I take all possible interaction constants, so I get a bunch of n by n matrices, and that's x of n. And we're going to see on the next slide why it's kind of important and natural to also introduce the closure of xn. So xn itself is a bounded but not compact set of arguments. So xn bar is just the closure of xn. For example, when n is equal to 2, you look at planar graphs with 2 boundary vertices. So here are 2 examples, and the boundary correlation matrix is a 2 by 2 matrix, where there is only one interesting entry, which is the correlation. And in this case, it's very easy to compute from these formulas that the correlation is just this hyperbolic tangent. So it's the denominator is the partition function, right? There's 4 spin configurations, 2 of them have weight exponential of j, the others have a weight exponential of negative j, and the numerator is what you get from this formula, essentially. So it's not really important. What's important is that this, as j goes from 0 to infinity, m takes all possible values between 0 and 1. So already this graph alone gives me almost all possible boundary correlation matrices. Now, if I send m to 0, then in the limit I get the graph on the left, where the correlation is 0. And if I send j to infinity, then I don't get any graph related, but the correlation tends to 1. So the conclusion is that the space x sub 2 is a half-open line interval, and its closure x2 bar is a closed line segment from 0 to 1. And more generally, x of n is going to be some bounded subset of full-dimensional subset of R to the interest 2, which is it's going to have some of the boundaries, but not the rest of the boundaries. So it's kind of a weird in-between subset. And then the only thing you need to allow to pass to the closure is you need to allow having infinite interaction constant. And when an edge has an infinite interaction constant, it corresponds to just forcing the spins at the endpoints to be the same, which is kind of like a contracting this edge, except that if the two vertices are in the boundary of the disk, when you contract, you don't get a disk. You get some kind of a weird cactus, whatever. But that's the only thing you need to do. And then you get all points in closure. So I think I'm done with the Ising part for now. Let me quickly switch to total positivity, and then I'm going to explain how they are related to each other. And there are many interesting totally positive spaces. So I'm going to be focused on the totally non-negative Grassmannian. I'm not going to say totally non-negative all the time, so I'm going to abbreviate it as TNM. TNM means totally non-negative. And the usual Grassmannian is the set of all k-dimensional linear subspaces of R to the n. Alternatively, you can think of it as the space of all full rank k by n matrices modular row operations. And the connection between these two definitions is that given a subspace, you can pick a basis. That's going to be k vectors in R to the n. So you put them in a matrix, and then you get the second definition. Or conversely, given a matrix, you can take the row span, you get the first definition. For example, the row span of this matrix here gives you an element of the Grassmannian of 2-dimensional planes in 4-dimensional space. And it's usually convenient to think about the elements of the Grassmannian, not in terms of matrices, but in terms of Lusztig coordinates. So a Lusztig coordinate is the following thing. You take your k by n matrix, and you pick k columns of this matrix, and then the corresponding Lusztig coordinate is the determinant of the k by k submatrix with using these columns. So there's n choose k different Lusztig coordinates, and for this matrix here, all Lusztig coordinates are shown on the right. So for example, delta 2, 4 is the determinant of the red submatrix with columns 2. A definition which is due to Postnikov is that the TNM Grassmannian, or the totally non-negative Grassmannian, is the subset of the usual Grassmannian, where every Lusztig coordinate is non-negative. Yeah, so because these Lusztig coordinates are defined after a scaling, you should actually say that they are all on the same side. But you can, after some operations, you can make them all. But is that what was the question?
Are you taking Grassmannian or always Grassmannian?
I'm taking the first one. So I'm taking the subset of the unoriented Grassmannian where all Lusztig coordinates are the same sign. This is well defined subset. For example, this matrix here, its row span is the element, well, you can see that all Lusztig coordinates are non-negative, so it belongs to the TNM Grassmannian. Let me give you some intuition of how I think about this space. Let's say I take the same matrix and the same Lusztig coordinates, and instead of thinking about the rows of the matrix, I'm going to think about the columns. So let me denote the columns by U1 through UN. These are vectors in R to the k. And in this case, they live inside the plane, so I can literally draw them in the xy plane. And having delta ij being positive corresponds to ui and uj being labeled counterclockwise. Or in general, having the positive Lusztig coordinate corresponds to these columns forming a positively oriented basis of R to k. And because all the deltas here, delta ij's are all positive, it means that the ui's have to belong to the same half plane and be labeled counterclockwise.
So you take any pair of possible cases, you take it in the order they found the matrix.
Yeah. But then, of course, some of the ui's can become parallel or even zero, which would send some of the deltas to zero. But you cannot just pick an arbitrary set of deltas and send them to zero because they are not algebraical dependent. They satisfy the Kluger relations. And in this case, there is only one interesting Kluger relation, which tells you that 1 times 3 equals to 2 times 1 plus 1 times 1. So the CNN Grassmannian somehow is the configuration space of moduli space of such vector configurations. And it has one top-dimensional cell where all the Kluger coordinates are strictly positive, which corresponds to generic vector configurations. And then everything else happens on the boundary. So there are boundary cells of dimension 1, where just one delta is 0 and the rest are strictly positive. And here, for example, delta 1, 2 is 0, or I could have delta 2, 3 being 0, or delta 3, 4 being 0, or delta 1, 4, and that's it. I cannot have delta 2, 4 being 0 and the rest positive because, well, for instance, it violates this Kluger relation. But I can have delta 2, 4 being equal to 0 in a cell of codimension 2. For example, here delta 2, 4 is 0, as well as delta 1, 2, and delta 1. This is a cell of codimension 2. And you get some interesting combinatorics of these boundary cells, which was developed by Postnikov, and he gave parameterizations of these cells using some combinatorial objects. In particular, it follows from his work that every boundary cell is an open ball topology. Right, so just pick some Kluger coordinates and set them to 0, and the rest to be strictly positive. What you get is either the empty set or an open ball topology. But he conjectured that the closure of every boundary cell is a closed ball. Right, so some deltas have 0 and the rest are negative. And this conjecture, there has been a lot of progress, for example, due to Williams and Postnikov's Williams and Rich and Williams, who, by the way, proved that the closure of every boundary cell is contractible. And notice how this conjecture, there is one very special case where there is one top-dimensional cell whose closure is the whole CNN Grassmannian. So this conjecture is saying that the CNN Grassmannian is a closed ball. And last year, Stephen Karp, Thomas Lam, and I would prove this special case of that conjecture. Right, so the CNN Grassmannian is fundamental to the closed ball of appropriate dimension. And then we worked for a year, and recently we were able to finish this conjecture in full generality. So the closure of every boundary cell is indeed a closed ball. And these two theorems, well, they have completely disjoint proofs. First of all, the first theorem is, the proof is pretty elementary. And it's going to be important for the Ising model. So I'm going to tell this proof to you later on. The second theorem, it involves some heavy results, like some affine flag variety stuff, and also we don't know how to avoid the Poincare conjecture in all dimensions. So the version that we're using is that given a compact and factible topological manifold of the boundary, such that the boundary is a sphere, then the manifold has to be a closed ball. And then there's a lot of flag variety calculations after that to show that the Grassmannian is all. But the reason we got interested in these questions in the first place was because we were studying the amplituhedron. So there is this physical object or geometric object which helps you compute scattering amplitudes for the angles for supersymmetric angles here. It was recently discovered by Arkani and Trinka, and it's essentially just a linear projection of the TNN Grassmannian, much like it literally generalizes the construction, but the whole itself is a linear projection of the simplex. And there is a more recent story, which is an analog of this for n equals 6. This is called the ABJM theory. And in this case, instead of the TNN Grassmannian, you just look at how these cells stick together, and you get the TNN orthogonal Grassmannian, which is going to be the main player of this talk. So let me tell you the definition of the TNN orthogonal Grassmannian. First of all, recall what is the usual CNN Grassmannian subset where all Lusztig coordinates are negative. And then the orthogonal Grassmannian, well, it's an old object, and usually people define it as the subset of the Grassmannian where a certain symmetric bilinear form doesn't vanishes. But if you pick a specific bilinear form, you can arrive to this definition here, which is in terms of Lusztig coordinates. So the orthogonal Grassmannian is a subset of Grassmannian of n by 2 n matrices, where every Lusztig coordinate is equal to the complementary Lusztig coordinate. So the determinant of any n columns is equal to the determinant of the remaining n columns. And then the definition, which is due to these physicists Huang and Wen, is that the TNN orthogonal Grassmannian is just the intersection of these two spaces. Or to spell it out explicitly, the TNN orthogonal Grassmannian and 2n is the subset of the Grassmannian where every Lusztig coordinate is equal to the complementary Lusztig coordinate, and both of them are negative. So, and here, square brackets 2n means just all integers between 1 and 2n. So the Grassmannian, in this case, has dimension n squared, and the orthogonal Grassmannian has dimension n just 2. So it's a roughly half-dimensional piece of the CNN Grassmannian.
I is an arbitrary and element subset.
Yeah. Yeah. So it's a half-dimensional subset, essentially. And it has some boundary specification which comes by just taking the specification for the CNN Grassmannian and intersecting. Okay, so now I think I'm in the position to tell you the main result of this talk, which is the relationship between this Grassmannian story and the Ising model story. So for the Ising model, remember we were studying these spaces xn and xn bar here, which one of them, well, they're just spaces of boundary relation matrices of planar Ising networks. And they live inside the space of symmetric n by n matrices with ones on diagonal. So first of all, I'm going to define a certain map called the doubling map. This map, it takes an n by n matrix and produces an n by 2n matrix. And the reason it's called the doubling map is just because it doubles every column. So you just take the first column and you literally make 2 copies of that column, except that you put some signs in there. There's a very simple rule for the signs. You just put them in an alternating way, like left, right, and left, right, and left, and left. Something simple like that. And you just do it for columns 1, 2, 3, and 4, and that's it. And the first kind of simple observation about this map is that it embeds the space of such matrices as an open dense subset of the orthogonal Grassmannian. Right, so both spaces have dimension n just 2, and this is kind of like a sugar cell, you know what it is. And then inside of these matrices we have the space of planar Ising networks. Inside the orthogonal Grassmannian we have the TNN orthogonal Grassmannian. And the main result is that the doubling map gives you a homeomorphism between these 2 spaces. So they're essentially the same. And the second main result is that both of the spaces are homeomorphic to an n just 2-dimensional closed form. Let me show you an example of what this theorem is saying for n equals to 2. For n equals to 2, we were looking at planar Ising networks like this one, where your boundary correlation matrix is a 2 by 2 matrix. And here m has to be between 0 and 1 if you want your matrix to belong to the space x to the power. Now if you apply the doubling map, you get a 2 by 4 matrix. So let me compute the Lusztig coordinates of this matrix. Here they are. So I just computed all 2 by 2 determinants of this matrix. And the first thing you see is that every Lusztig coordinate is equal to the complementary Lusztig coordinate, which means that this map always ends, like for any m, we end up inside the orthogonal Grassmannian. But now, if you require all these deltas to be non-negative, then this happens precisely when n is between 0 and 1. Right? Because of these two inequalities here. So this matrix actually belongs to the TNN orthogonal Grassmannian, and then you need some work to show that every matrix in here, after some row operations, can be transformed into a matrix like this, or M. This is true. And so that's the main result for n equals to 2. And by the way, this is the answer to the question from the first slide. Remember, there was a question of how to describe boundary correlations of planar Ising networks. And the answer is, well, okay, the edges of this matrix are correlations, boundary correlations, and these deltas are polynomial functions in these correlations. So we just require all the deltas to be non-negative, and then this cuts out precisely this space of boundary correlation matrices. Okay. So now I think that was the main result, and let me now tell you the second main result, which is the relation between this story and this Kramers Lanière's duality, which on the history slide, it was somewhere over here. Right, so they were the first guys to compute the critical temperature for the square grid. But actually, their construction works not just for the square grid, but for arbitrary planar Ising networks. So let me explain it to you in full detail. So here's what you take here. I'm going to take a planar Ising network, and I'm going to produce another planar Ising network, whose underlying graph is going to be just the planar dual of my original graph. And so every edge gets replaced by the dual edge. And again, I'm going to get n boundary vertices. So basically, the only thing I need to tell you is how do I define the dual interaction constants. And the dual interaction constants are defined using this equation. For every j, for every positive real j, there exists a unique positive real j star such that this equation is satisfied. And this is kind of odd, but we're going to see later on why this equation is important for the Ising model. And okay, so here's a question. What happens if I apply this duality 2 times? Yeah, of course I will get back to my original planar Ising network, right? I mean, I get the same graph, and I get the same interaction constants, but I claim that still these two pictures are not actually the same. I don't know if you can spot the difference. Yeah, so the difference is that the boundary vertices are labeled in a different way. Right, this labeling here is a cyclic shift of this labeling here. And this is important for us because we care about boundary correlation matrices. So this planar Ising network has a different boundary correlation matrix than that planar Ising network. And the reason that this happens is that when we apply this duality, we need to pick a rule of how we label the new boundary vertices. And here's an example of such a rule. You could say that the new B1 is obtained from the old B1 by going counterclockwise. But then if you apply the same operation again, the next B1 is again going to be counterclockwise from the previous one. So this is where you get the cyclic shift from. So the conclusion is that the Kramers-Lanière's duality is some operation on boundary correlation matrices such that it's the square root of the cyclic shift. And so it has, in particular, it has period 2n. Now let me say a couple of words of why this map is important for the Ising model. Recall the same equation. First of all, most importantly, it preserves the partition function. More precisely, there are two natural expansions for the partition function called the high temperature expansion and the low temperature expansion. So this duality switches between the two expansions. And also it takes these correlations that we care about to something that's called disorder variables. So it takes important things to other important things, as a good duality should do. And also, if you want to find a j that's fixed by this duality, so you want to find the interaction constant with the temperature which is fixed, then you get precisely this critical temperature for the square grid. And if you take the square grid itself, then the planar dual of the square grid is just a little bit shifted square grid. So if your graph is large piece of the square grid, then its dual dual is going to be very close to G in modulus and boundary corrections. So a vague philosophical observation here is that when we're taking these pieces of the square grid and we are setting all the interaction constants to be just critical temperature, we're trying to find some planar Ising network that is fixed under this duality. And this is not a theorem, this is just some kind of observation, but I'm going to try to make this more precise later on. Okay. Now let's see what happens on the Grassmannian side. On the Grassmannian side, we have this theorem that CNN Grassmannian is a closed ball. And the proof of this theorem, which I promised was elementary, goes as follows. We just construct a certain vector field on the TNN Grassmannian, and this it gives you a flow, and this flow contracts the whole TNN Grassmannian to just at one point in the interior of the TNN Grassmannian. And this flow involves a cyclic shift, and this point is the unique cyclically symmetric point inside the TNN Grassmannian. So here, by the cyclic shift, I mean just the map on K by N matrices that takes the last column and moves it to the first place. Just cyclically permutes the columns of the matrix. And there's also a sign because, well, you want this map to preserve the TNN Grassmannian. And it's very easy to check from linear algebra that if all Poynting coordinates of this matrix are negative, and then the same is true for all Poynting coordinates of this matrix. So, okay, and now we know there is a Brouwer fixed point theorem that given a continuous map of a ball to itself, it must have a fixed point. But the miracle here is that it has exactly one fixed point. And so for the CNN Grassmannian 2,4, I claim that the fixed point is the row span of this matrix. So let's, if we apply the cyclic shift, we take the last column, move it to the first place, and change the sign because K is even. We get a different matrix. And if you draw the column vectors in the xy plane, then this is the picture you're going to see. These are some vertices of a regular A column. And because these two pictures are related by a coordinate transformation, these two matrices are related by sequence of row operations. So this matrix gives you the same element of the CNN of the Grassmannian. And the other way to see that these two matrices have the same row span is to just compute the Plucker coordinates. For either matrix, Plucker coordinates are going to be the same. And you can see that they are all positive, so this belongs to the interior of the TNN Grassmannian, and they're all cyclically symmetric. So this is a cyclically symmetric point. And also notice that every Plucker coordinate is equal to the complementary Plucker coordinate. So this matrix here belongs to the TNN orthogonal Grassmannian. And in general, the TNN orthogonal Grassmannian is invariant under this cyclic shift. So you can just take the same proof and literally apply it to the TNN orthogonal Grassmannian, and this is how you get the second part of this theory. Right? So the second part is an easy consequence of the first part together with this proof. And now let me tell you the relationship between this Kramer's one-year duality and the cyclic shift.
Sorry, you're going to construct it. Tell us how you construct it.
Well, so it's just, you just multiply your matrix on the right by exponential of t times the second cyclic shift. So it's like the integral vector field. The flow is just the integral flow of this vector field, which is here. Each of your vectors of your vector configuration tries to chase the next vector. So this, in the end, it's not trivial to see why they all tend to the same way. Okay, so the relationship between the duality and the cyclic shift. The Kramer's one-year duality acts on the space of planar Ising networks, and the cyclic shift acts on the TNN orthogonal Grassmannian, and the claim is that the Dublin map translates one into the other. So the diagram is commutative. And notice how both of these maps, they have period 2n, which is good. This is a commutative diagram. And one nice corollary of that is that here in the orthogonal Grassmannian, we have unique cyclically symmetric form.
So if you was to double that,
yeah, Phi is the Dublin. And by just taking the image of this point, we get that there, for every n, there exists a unique boundary correlation matrix that is fixed by this Grassmannian duality. So for example, for n equals to 2, this graph gives me, this planar Ising network gives me this matrix M naught, if and only if J is the critical temperature of the square grid. And this is how we arrived to this second part originally. We just took the pre-image of this special point and we saw critical temperature. For n equals to 3, you get the critical temperature for the triangular lattice and the hexagonal lattice simultaneously. And so, okay, so now this claim, this vague observation becomes a little bit more interesting, because now, instead of looking for something that's asymptotically fixed by this Grassmannian duality, we actually get one fixed point for every n. So we can work with actual fixed points of this duality. And now, okay, let me try to make this into a precise conjecture. So let's say I take a unit disk, and inside of it I take a small square grid. So this is going to be my G, and then I'm going to just take all the J's, all the interaction constants to be the critical temperature. So this gives this a planar Ising network, which has a boundary correlation matrix M of G, J. Now this is going to be an n by n matrix, where n is whatever the number of boundary vertices. There is another matrix, which is this matrix M naught, right? The unique matrix fixed by this duality from the previous slide. And it also exists. There's also an n by n matrix M naught. So I'm going to try to compare these two matrices with each other. And the entries of M naught are actually easy to compute, sort of. Because this is a general fact about the doublet map. This is the inverse of the doublet map. Right? Given a matrix, you can write down every entry as a rational function in the Fluker coordinates, the element of the Grassmannian corresponds to. And in this case, the element is this special cyclically symmetric point. So its Fluker coordinates are actually very easy to compute. They're just products of the signs. This is the trigonometric van der Waals determinant. Right, so from here, you can see that they are all cyclically symmetric and positive. So the question is, how close are these two n by n matrices? And even more precisely, do they have the same scalar limit? And at some point, I realized you can actually test this conjecture on the computer. So if you write a simple program that computes these matrices using this formula for n from 2 up to 20, you get a picture like this. Right? So this is the plot of the first row of my matrix M naught, properly rescaled. And every other row is just a cyclic shift of the first row. Now this looks like a function, and on the other hand, if I look at this matrix M of G, J, and it comes from the square grid, and there is this conformal invariance for the scalar limit of the square grid, which in particular tells you the scalar limit of these matrices. And usually it's given for the upper half plane, in which case if your 2 points are distance t apart, then the scalar limit of the correlation between them is just 1 over t. And now if you Google or find a conformal map from here to the unit disk, then for 2 points that are distance t apart, the asymptotic correlation is going to be square root of 2 over 1 minus the cosine of t. So this is just the formula that comes out of all these conformal field theory stuff. And of course, if you plot that function, you're going to get this blue curve here. Right, so this question is actually a conjecture which relates this TNM Grassmannian to the Ising model of critical temperature. Conjecture is that these two matrices have the same scalar limit. And okay, so this was the second main result. And in the remaining 5 minutes, let me.
So the second result is the conjecture, or is the numerical?
No, the second result is that. This theorem, the second part of this theorem. And then the rest is just an interesting kind of speculation of where this would go eventually.
And so on the numerics, there were also some blue dots, so that was like
Yeah, so blue dots, the dots correspond to n from 2 up to 20.
red dots.
The red, the giant red dots are 20.
Okay, okay. So the limit.
So that's kind of confusing. But you can see the blue dots are a worse approximation of the plot red dots. Now, I want to spend the last 5 minutes on electrical networks. There seems to be a very strong analogy between Ising model and electrical networks, which was kind of undiscovered before, but just is obvious in our work. So, what is a planar electrical network? Well, it's the same thing as a planar Ising network, except that here on every edge you have a positive real number, which is the resistance of that edge. So you have a resistor network inside of this. And then every planar electrical network gives you an electrical response matrix. And so you apply some voltages to the boundary vertices, and then you measure the currents through these boundary vertices. So maybe you have some kind of planar brain and you want to know what's inside, but you're not allowed to go inside. And so you get some kind of map from voltages to currents. And this map turns out to be a linear map. Right? You can find the currents using these electrical laws, Kirchhoff's law, Ohm's law, and all of these laws are linear, so you get a linear map, and so you get a matrix.
It's a sort of discrete Dirichlet.
Yeah. And okay, so this is an n by n matrix, and again, surprisingly, it turns out to be a symmetric matrix. In this case, that's not true, obviously. And also, instead of having ones on the diagonal, it has 0 row sums. Right? If I apply the same voltage to every boundary vertex, I'm not going to get any currents. So these matrices also live inside an n × 2-dimensional space, but it's a different space of matrices. And inside this space, they form some kind of a non-compact subset again. So, but in this case, it's not enough to just take the closure. You need to take compactification. So you need to embed this somewhere else and then take the closure over there. I'm not going to go into that, but this was done by Thomas Lamb. He defined this compactification of the space of electrical networks. And then let me compare this space En bar with the space Xn bar of planar Ising networks. It turns out that they have the same stratification. So the boundary stratification of Xn bar comes from the theorem of Grassmannian, or you can define it directly in terms of planar Ising networks. And the same stratification works for the electrical networks. And in either case, there's one cell for each matching of 2 endpoints in the circle. So every matching of 2 endpoints in the circle gives you a cell here, which of dimension equal the number of crossings of that matching. So for example, for n equals to 2, here's what we saw. The space X2 bar was a line segment, and it has a stratification into one-dimensional cell and 2 zero-dimensional cells. And the corresponding matchings look like this. This is a one-dimensional cell, a 0 and zero-dimensional cells. And these are all possible matchings of 4 points on the circle. And the same is true for electrical networks, everything. Here's the bigger picture for n equals to 3. The stratification looks like this. These are all possible matchings of 6 points on the circle. And there's always one top-dimensional cell whose dimension is n × 2, where you just match every point to the opposite point on the circle. And so this is one analogy between these two worlds. There is another analogy that there is this wide delta or star triangle, very well-known transformation for electrical networks. There is a much lesser known star triangle transformation for the Ising networks, which have the same combinatorics but different formulas. So the question is, can you find a change of code, like some kind of simple formula that takes you from planar Ising networks to electrical networks? And this seems like an easy question, but nobody knows how to do this. There's also a related second question, which is, can you show that the closure of every boundary cell is a closed ball? And the connection is that if you can prove this, then it's going to follow from some general full set topology results that such a stratification preserving homeomorphism must exist in general. It's not going to be explicit, but there's going to be some implicit But of course, it would be interesting to find an explicit formula, because these spaces have been studied for 100 years each. So I think this is it. The slides are on the website, the paper is on the archive. Thank you very much. I think the most general electrical network looks like this. I don't think you can make it into a star because it's going to be a 6-dimensional. I mean, we could try. I don't think there's too, you can reflect this with triangle. I don't think. Like, what would be the star in this case?
The one star that you can run. So the point in the middle, and the first star is over the other.
Like this?
Yeah.
But this is 4-dimensional. And this space is 6-dimensional.
But you can find those, we have the same response matrix.
Well, that's not true. The response matrix is form a 6-dimensional space. It cannot be, there is no injected map for 4-dimensional space. Yeah.
Again, that was also that was maybe a message. Did you say something with the number of vertices you get larger and larger?
So I'm only taking closures when n is fixed. But if n gets larger and larger, you would expect some kind of critical temperature phase transition sort of results, which yes,
what does that mean?
I don't know, but it seems from this relation that it should mean something. And nobody was talking about this.
So, before there's a connection between the nonnegative orthogonal Grassmannian and the Ising. Is there any conceptual reason to expect such a connection?
Not that I know. I have no idea why this connection. We just found it by accident. There seems to be another connection between these electrical networks and some kind of totally nonnegative isotropic Grassmannian, which is also.
Only the planar case.
Yeah, that's all planar theory, by the way.
Is there any relation at all between the totals you used and those that Carol used?
No, I don't think there is any. That thing is much more complicated.
There are no other questions. We'll take our